Nice to meet you too.
So I guess they say you want to take some more math classes, right?
Yup.
Now I put the couple in there. I guess your father, is that who I was emailing?
Yup.
I put a few in there as far as what I think you could do next. Did you see those? Did you talk to him about those courses?
A little bit, but not that much.
Okay, so we have a couple courses that you might be interested in. Have you done any proof type things with mathematics?
Not yet, but I'm sure I'll need to be prepared for that a little soon when I get into things like the USAMO.
Sure. Well, we're not going to train you for those, but we'll just give you the mathematics courses. So there's overlap, of course, but they're not aimed at math competitions. So we have a couple courses you may be interested in. The one was Calculus 3, and the other was something we call Transitions to Higher Math, and that's kind of a proof class.
All right. So what kinds of content are included in Calculus 3?
So you took Calculus 2?
Yup.
Well, you took the BC, according to the typical Calculus 2. So in Calculus 2, you ended with, do you remember some of the topics you ended that course with?
Yeah, mostly what I remember from the end are like Taylor and Maclaurin series.
Sure, Taylor and Maclaurin are near the end. Did you do anything like parametric equations?
Oh, yes, we did.
So nearly, I don't know, every book's a little different, but most of them have near after the Taylor and Maclaurin, you do a little bit of the parametric equations and a little bit of polar coordinates.
Mm-hmm.
And what we do in Calculus 3, we take the calculus that you learn in Calc 1 and 2 and apply it to multi-dimensional. So you have a y and an x, so now you might have a y, x, and a z, or more variables. And what we need the parametric equations for is to represent equations in multiple dimensions, like x, y's, and z's. And then we also need polar for some of the problems that we run into are a little bit more difficult. So the polar coordinate is a tool to help us make some problems a little bit simpler. Okay?
So, do we cover spherical coordinates in that topic, or?
Yes, sir. Yes, sir. Spherical is in there, and the calculus of spherical coordinates would be in there. And you do parametric and polar and spherical and cylindrical when you get to 3 dimensions.
That sounds like a good choice.
Yeah. And then we have the other course is Transitions to Advanced Mathematics, which would be introductory proof class. And so you've probably done geometry proofs or something like that before?
Not really.
You haven't done any proofs before? Maybe we'll have to see what kind of proofs you can do, which proof class we put you in. I also put the times on there. I don't know your schedule with high school. Do those times work for you or not? Or do you know if that would be feasible?
What are the listed times? Can I look at them again?
Sure. I'll tell you what they were.
Your high school time is from 8 in the morning to 3 p.m.
Okay. So these were, I'll put the times in the chat. They're twice a week. And
did you send them? I can't see them.
I'm getting them. I put them in the email, but I'll put them in the chat here in a second.
All right. Okay.
So one class is Monday, Wednesday. That's the Calculus 3. And the other is the proof class we call Transitions, and that's on Tuesday, Thursday. Do either of those times work for you?
Sadly, they don't, because my classes are from 8 to 2:30, so.
8 to 2:30. Well, I can see if there's anything that works for you. Those would be kind of the sensible next ones to take.
Yeah?
And the distance from our home to the college is about 30 minutes.
About 30 minutes, okay. We do have remote classes. I don't know exactly if that could work with school at all. That would be during the school hours, but then you would just have to log into the computer.
Are they the same times as the regular classes?
Well, different things. We have linear algebra, which is 11:20 to 12:50.
Okay, and the other one?
And
okay.
we have discrete math.
Linear would be more interesting.
Yeah, I guess. I'll see if I can make time for either of those.
Yes, we're gonna talk to the principal, whether the principal allow you to give you like the to participate in those classes twice a week. So
you guys let me know what you can do with the school, and there is. Like I said, these are in person. These two courses are in person. So you let me know what you can do with the school. If the school says you can, I guess we can't. But if there's a way to do it, we have these two, which I think would meet your needs, Subornos. So that would kind of fall into the line of your next steps in mathematics development. So those will be probably the best. We have another course, linear algebra, which our number for that is MA3160, and this is remote, so that would mean it would be like a Zoom class. But let me see the time for that. It's Monday, Wednesday, 11:20. So this is the third class you could consider. And this one is 11:20 to 12:50, and this one is remote. So the first two are in person, and that third one is remote, which would mean you would Zoom in to a professor like this. So that might be possible, more possible to school, or maybe not, I don't know. Which school did you say you went to?
A school called Malvern High School.
Malvern, okay. Well, we could...
We'll check with his principal, and we'll email it to you, and we'll CC his principal.
Okay, that sounds good. Yeah, just let me know what's up, and we can work with your needs as best we can. And maybe if you do decide to come before we do the discrete math, before you do the proof class, if you are going to do that, we'll talk to you about how to prepare for that. It's not particularly hard, but it's a different way of thinking than you did for the calculus or the computational math. So your brain is all set for calculations, but the proof type thing is a little different. So you think a little bit more to the logic and less to the computation part of your brain. So if you are going to do these, we'll talk a little before you get into the... There you go. Here's a nice simple one for you.
Okay. Non-zero coefficients polynomial are all replaced by their mean to form a polynomial Q. Which of the following could be a graph of y p of x and y of q of x? The interval. Alright. Oh, not that one. Guess I can share screen via cable. Oh, can't start screens here. So, I guess I can try it. So, let's see. Q of x is all going to have the same coefficients, so like m times x cubed plus x squared plus x plus 1, while p of x is going to have a bunch of different ones like, I don't know, ax cubed plus bx squared plus cx plus d. So let's try, for example, a quadratic case. Let's let q of x be mx squared plus mx plus m, and p of x is x squared, or ax squared plus bx plus c, where a plus b plus c over 3 equals m. So what can I do here? Well, a plus b plus c then has to be 3m. Oh, okay. So that means we have a plus b plus c over 3 times x squared plus x plus 1. Let's look for the intersections. So, for example, we have a plus b plus c times x squared plus a plus b plus c times x plus a plus b plus c equals 3ax squared plus 3bx plus 3c. So ax squared plus bx squared plus cx squared plus ax plus bx plus cx plus a plus b plus c equals 3ax squared plus 3bx plus 3c. Wow, this is pretty tricky. So 2ax squared plus 2bx plus 2c. So bx squared plus cx squared plus ax plus cx plus a plus b equals 2 times ax squared plus bx plus c. Wow, that's hilarious. So where are they all going to intersect? That's pretty tricky. So what is something with all the same coefficients going to look like? You can see my application?
Pretty good, yeah. Let's see.
Okay, so let's see. If I have something like this, so, I mean, I don't want to go through casework, but...
Well, tell me what you were thinking. Tell me what you were thinking and go slower.
I guess I was trying to find where all the intersections could be, so I took just a quadratic case and set the equations equal to each other.
Okay.
And I'm trying to see if I can find anything. So ax squared plus bx plus c, a plus b plus c over 3 times x squared plus x plus 1. So how am I going to find these? Well, for the case of x equals 1, they're all going to be the same. For the case of x equals minus 1, this becomes 1, this becomes minus 1. Okay, so for the case of minus 1, we have a plus b plus c. 3. For the case of 0, they're not going to be the same. This is going to be 1 minus 1. So it's going to be a plus b plus c over 3 times 1 equals a minus b plus c. So from what I can find, they have to intersect at 1.
Okay, so then start there. Look at your graphs. Oh, do you have it?
Yeah.
Okay.
Alright, so that one doesn't intersect at 1. That one intersects at 1. So none of them intersect at 1 except B. So I'm going to say B.
There you go.
There we go.
Okay, that was good. Let me ask you another question. Do you know what an even number is?
I'm pretty sure I do.
What's an even number?
It's a number that's divisible by 2, or it's a proper multiple of 2.
Okay, so it's a number that's, this is a very easy question. So if I take 3, that's divisible by 2, right? Because I can take 3 would equal 2 times 3/2.
Oh. Technically, I guess an even number would be a number such that 2 is a proper divisor.
Okay, so then maybe it's 2 times some whole number or integer or whatever word you use. Have you heard the word integer before?
Yeah.
What's an integer?
An integer is, that's hard to define.
Well, give me some examples. Tell me what you know about integers.
Well, an integer is something where, an integer can be expressed as a fraction like this, such that A is, or B is a proper divisor of A. But then again, that's kind of like circular definition, because a proper divisor is,
Sure. I don't need the definition. We can worry about a proper definition, a rigorous definition later. But what are the numbers that are typically integers? What numbers do we mean?
Numbers that don't have any digits after the decimal place, or any non-zero digits after the decimal place, like 4.
Okay, so if we write it as a number, it's 67 and 4 would be fine. Is 0 and then integer?
I think so, yeah.
And -4, is that an integer? Okay, so it's all the -4s and the 0s and the -67s. And we can talk about where they come from later, but at the moment, it's the set, you know what they are: 0, 1, 2, 3, and -1, -2, -3, right?
Yep.
So if you write down n is even, write that down. If and only if.
Okay, wait, what?
If and only if.
If and only if. I'm pretty sure there's a logic symbol for that, but...
Yeah, there is. There's a couple. If and only if n equals 2 times k.
Oh, okay.
Where k
is an integer?
Okay, so that's how we define even. And so you can even say at the beginning, let n be an integer, because we're just talking about integers. What do you think odd would be?
Oh.
No, you have it right. Even is good, but if I were to write a definition for odd, what do you think the definition for odd would be?
N is odd if and only if n equals, I don't know, k plus 1, where k is an even integer.
Okay, something like that would work. I think typically we'll start with something like n is not even. Or we could write n equals 2k plus 1, where k is an integer.
Yeah.
So have you seen the representations like that, 2k plus 1 to represent odd numbers?
Yep.
All right, so let me ask you this. This is very simple, so this might be new to you, but it's very simple. Let n be an integer. If n squared
Jesus.
is odd,
then n is odd.
You think you could prove that?
Maybe.
You want to try, or do you want to think about it and just talk to me later?
I'll try. So 2k plus 1 squared is equal to 4k squared plus 4k plus 1. And since k must be an integer here, then this must be even, because it's a multiple of 4, and 4 is a multiple of 2. And adding 1 to it changes its parity, so it goes from even to odd.
So what we want to do, though, is prove it. So we'll have to work a little on the way you work your logic through. You have the algebra down fine. We'll have to work a little bit on what we mean by the logic. A simple statement like this, you can do nicely the way you wrote it out, calculation-wise. But if they get more complicated, we have to be a lot more careful with the logic. So we'll talk a little bit about that at some point. There's another way to do this problem. Do you know the word contrapositive?
Oh, yeah. So basically, it's when you change everything in a sentence, but it still keeps its original meaning.
That's true, but it's a particular kind of sentence in a particular kind of way. Do you know what that is?
Wait, what?
Contra, C-O-N-T-R-A, positive.
So, for example, he is agile. The contrapositive would be he is not slow.
Okay.
I guess.
No, not quite. How did you get he is not slow? Tell me what you're doing.
Because agile is the antonym of slow. So these two are essentially saying the same thing, but one is stating what he is, and the other is stating what he is not. Okay,
not quite. So in mathematics, contrapositive, a very particular type of statement. Take it, if P, then Q. Write that down.
Okay.
And then if I write, if not P.
If not P, then not Q.
And these are logically equivalent. Meaning whenever the first statement is true, the second statement is true. And whenever the second statement is true, the first statement is true. And that's always the same.
Wait, but I have a question about that.
Yes, sir?
So what if two separate events cause the same thing? So if P, then Q, and if R, then Q. Then the statement if not P, then not Q wouldn't be true because you can still execute R in order for Q to be executed.
It's not a computer program, it's just logic.
Alright.
Yeah, is that where you're getting that executed from and all that?
Sort of.
Yeah. Did you learn programming?
Yeah, a long time ago. I've forgotten most of it.
That's fine. I'm not going to test you on that. Just curious what you've seen. So we have the statement, if n is, or what do we say, n squared? N squared is odd. Then n is odd.
Oh, so if n squared is even, then n is even. Or if n squared is not odd, then n is not odd.
Yeah, so write the contrapositive, right? If n. No. Look at the statement above. Oh, hold on. It's not Q. Hold on. Go back up to your statements. It should be if not Q, then not P.
Oh, okay.
I don't know if I said it wrong or you wrote it wrong, but either way, we as a team got it wrong. If not Q, then not P.
Oh, okay. That makes sense. Oh, yeah, okay. That clears up the question there I had a little bit.
I see why you're asking the question now, yeah.
Okay. N squared is not odd. If n is not odd, then n squared is not odd.
Yeah, so that's it's a different statement, but they're equivalent. So then I can write even, right? If n is even, then n squared is even.
So if
So in this case here, we'd be very careful and we would say, let n be even and then show that n squared after I squared it, you still get an even number. So the goal in this course transitions is, you're expected to know this kind of thing walking in, but we'll hammer the logic in your head a little bit better so that you think this stuff through a little bit clearer. So the goal isn't so much that this is a hard statement. The goal is to learn how the logic works. So as the logic gets more complicated, you have to write it out a lot more carefully because no mathematician can keep it all in their head.
Yep.
So, okay. So, well, it was nice to meet you.